My name is Swarnava Chattaraj. I'm currently in the diploma level of the IITM BS program in data science. Today, I think the title was an effective theory approach to deep learning that I will be going to present. Okay, so mostly I will be writing them down, and the things are a little bit dense, so I will be looking at my notes. So if you see me looking elsewhere, then I'll probably looking at my notes. Okay. Also, I should thank the PySquare seminar team and the ML series team for giving me this opportunity today. And happy Diwali to everyone. Everyone enjoyed the Diwali. Okay, so without any further distractions, let's get into it. So here there is this image that I have kept, although this is just for presentation purposes. I'll not be using this image too much. The topic will be to develop. So the plan for today is to develop the MLP iterative equation. This is nothing but the multi-layer perceptron short form. So I'll be referring it as MLP only, and then I'll give a short preview of vanilla gradient descent, and then I'll make one comment about backpropagation. Either formally, depending on what amount of time I have left, formally or informally, show that comment on hyperparameter initialization, and maybe this is depending on what amount of time I have left, I will be going into deep linear networks a little bit. So that's the plan for today. Do I have to say something? Okay. All I really need as prerequisites is knowledge about a little bit of multivariable calculus, only the differentiation, and very elementary probability. Although just knowing that the Gaussian distribution has a very canonical extension in the multivariate setting too. So, I mean, anyone, I'm expecting most of the candidates to be from the IITM BS program. So, anyone who has really attended the Stats 2 and MLF should have almost all the background necessary for today's talk. So, okay, now I'll come back to this picture. Today, I think I have shared it in the Google Messages or whatever, Google Chat, Meet Chat or whatever, the book that I'm actually following. So today's lecture is mostly on the second chapter. So whatever I tell, you will find almost everything there, except one thing that I will provide, except this one. You won't find this. They have commented on it, but they have not introduced it yet in this chapter. They will probably do it later. And this picture is also taken from that book. Okay, so the idea of the iterative equation is that every input, so this, each of them is one instance of input. So to give them a weightage and then push them, give a weightage to each of the inputs, and then have some nonlinear activation, and then whatever you get, use those as input for the next layer, and you iteratively build your model. So formally, we start by defining. So once I will do it for the first layer. So now there is two terminologies that will cause a little bit of issue. So once I do this weighting of the inputs or the weightage of the incoming inputs, I will name them as Z. So Z of some, so I will name them as Z, and then after the nonlinear activation, I will denote them as A. So you generally understand this is what my notation would be like. In fact, my X are from some Rn. So now there is this notational issue that I will be deviating from the book, that is the following. The book denotes the first so X is in Rn, so it's a n dimensional vector, so there are n components to it. So the book goes by, so there are now some nd number of inputs. So the alpha th input, and that's X alpha, and then the component, because each X alpha is an n dimensional vector, so they generally denote it like this. Mostly I will stick to this one. So that is one small notational deviation that someone might find. Nevertheless, so my X alphas are from Rn, and then each, also I want to make a note here that this picture shows that there are same number of neurons in each layer. Now that is just schematic. There is no restriction that the number of neurons in each layer has to be equal. They can be of different. So generally for the Lth layer, the number of neurons in that layer will be denoted by NL, the small NL. The capital was for the number of inputs you have in your data set. So your data set is typically this. That's the typical notation you have. With that, I think I have named everything. I'm not writing them very formally, but okay, never mind. So first I'll do for the first layer, and that will be, you will have some basis weights assigned to each of them. And then you will have a bias corresponding to each one. Similarly, for the next layers, so this is the layer next to the input layer, and for the remaining layers, one will have something like this. So this is your nonlinear activation, and you will have some incoming. So you have some ZJs here. So that's your the nonlinear activation. You will have it here. Let me write it this way. That will be better, I guess. So AJ -1 plus DIF. This is for all L greater than 1, and where your AJ is defined as some nonlinear activation of your ZJ. So those are, with that you have your iterative equation for the MLP. So okay, you would have to define, these were also part of the definition. So your each of them, okay, one small thing. So these are functions. So you operate some function. So it's like I'm defining a new function as this, sine composed cos. Now you operate them on some particular value. So like this, and then what you will have is sine of cos of x alpha. So really, I have not written on what these are operated. So I should actually mention that you have something like this here, but I didn't mention them to show you how the functions itself are composed, which is the more important part. In fact, I will almost never write on what particular test data it is operated on. I will generally just write down the function compositions. Essentially, this is nothing but the function composition. So I will almost never mention on what test data it is operated on. That is to be understood throughout the talk. So if we have this, then the actually main part of today's presentation is to develop the gradient descent. So how gradient descent works on the training of MLPs. The vanilla gradient, so the idea of a gradient descent is that if you have some parameter theta at some time t plus 1 and you have some loss functions which are parameterized by theta, so the gradient descent will look something like this. You have some step value and then at t equal to t. So this is what the gradient descent says. This is the gradient descent equation, and then you would have some loops, of course. If you are writing a program, generally the loops you have to just put the first order condition because you don't know where it will convert. So you will have some first order condition that wherever your gradient is 0, and then that leads into two issues, that gradient descent, the convergence of gradient descent is not guaranteed for non-convex optimization problems, which is one issue of deep learning in itself. But whatever, we'll stick to that only. But this time, okay, now I actually missed to make the following comments. So we'll do the same thing but on the MLPs. So for that, I have to first make sure what are my parameters. So the parameters are the following. You have quite a big list of parameters. So you see, for each layer, you have a matrix, which is nothing but NL-1 cross NL. For the Lth layer, you have a corresponding matrix, because this I have written for each individual neurons. You can have a corresponding equation in matrix form. So each of the values of the matrix are all parameters of your entire MLP. So to write that would be a little difficult, so I have to be very much schematic. So you have this, and then you have your I and j. So I goes from 1 to NL-1, and j goes from 1 to NL. 1 to NL-1, and j goes from 1 to NL. So these are very bad schematic notation, but that's for the first layer. And similarly, you would have L number of layers. So all those are your parameters. Then you have the biases. So you would have bi of 1. Your I will go from 1 to number of neurons in the first layer, and similarly you would have L many. Oh, you won't have L many, but you would have L-1 many, because in the last layer, so for the last layer, you don't have any bias, nor you do any nonlinear activation. Whatever output you have from the Lth layer, you use that as your output. I should have made that very clear, but I did not. Okay, so that with that, I'll actually start with the gradient descent business. Okay, so assume you have some trained function, or you have some initially function. So you have some f true, which itself is a Rn n-dimensional function, n-dimensional vector, and then you have your data set. So this is a very bad way of writing it actually. So maybe this, and you have some initial model which also is n dimensional. So not n, but this will be nothing but the number of neurons you have in your last layer, but whatever. And then you actually define some form of loss, which is a, so you have some loss function, you define it as, so you have some true. So in place of this, I'll mainly stick to some f. You have your x alpha, fx alpha minus, and in place of fmlp, you would have your last layer, and you would use some L2 norm. That's one of the choices. For example, you cannot do for any kind of norm. For example, L1 norm and L infinity norm, both are non-differential, both are not differentiable everywhere. So depending on what kind of norm you choose, the derivation that I'm going to work out will vary a little, but not too much. For example, the only change that you will find in my derivation and for some other p norm, where p is neither 0 nor infinity, is that is only for the last layer. And so for us, the gradient descent would look like this at some time t plus 1, and you again have some step size, and you want to do opposite to the gradient at some t equal to t. This is for all L from 1 to the last layer. And similarly, you would do the same for your biases, which are also part of your parameters. So that you have as of layer L at t is equal to t plus 1 is equal to time t. And you have some different step size. Okay. This is also for all L from 1 to N. Now I should stop here for a little bit, because is everyone with me? Like, have I missed anything, that have I said something that I have not defined it yet? So if anyone has found something like that, they can, question me, because have I defined everything, or is everyone able to understand what each of these mean? Yes, no, anything would be fine, but I need to know, because after a little bit, then restating what each of them mean would get out of hand. Okay, silence, I would take that as a yes, or everyone is bored out. Okay, whatever. So now for the last layer, we would, so I should start by making a comment here. So for the last layer, it's very as simple as I have written it here. So for the last layer, there is no issue. For example, to calculate this one need not make too much effort, because okay. So if I now, loss is a function of, so my loss was a function of z. So this is in vector form. Now that I was always, so in through the entire talk, you see, if I have not indexed something, that means I have actually contracted all the indices into a vector. And see, I have used norm. So in fact, this is equivalent to writing it in this form. So that's why in vector form I have written it as norm, and there I did not define it, which was again my fault. But so this, it is clear that my loss function is a, so this is constant because this is your true function that you are trying to estimate. For example, in your test data there will be labels for it, labels for each x alpha. So this fi of x alpha is the corresponding level of x alpha. So these are constant. So the loss function is apparently only a function of this, of the neurons of the lth layer, which I'll make clear that it is not, because it is intuitive enough, I guess, that this again depends back on L-1. But okay, still, since loss can be written as a function of the parameters zi's, so this chain rule can be applied. This evaluates to the following. This evaluates to minus fi minus zi of the layer L and your aj of the layer L minus 1. Okay, so this one you can write zi at the final layer as the summation of wij of that layer times a of L minus 1 j. J is equal to 1 to NL plus the bias term at the LF layer. So if you differentiate this with respect to wij, all you will get is 1 corresponding aj, and this is again a constant, so this will cancel out, and only one of this entire linear combination is actually dependent on this particular wij. So you would have something like, so the rest of the terms will cancel out, and this will evaluate to the following aj of L minus 1, and then you would have this partial differentiation which evaluates to 1. So that's how I get this aj L minus 1. So if that is fine, is that fine? Maybe yes. If anyone has any question, or if I'm saying something wrong, or if I'm writing something that I have not defined before, then please just knock me. So that, if that is clear, I will just leave this as an exercise for the viewers, that the following statement is also true. And in fact, I'm not writing on what I'm operating. So even this is a function and this is a function. So everything is written here is in the form of a function. If you want to know what one of their value is, you have to evaluate on a test point. For example, even here I have actually removed on what I'm operating, and I had actually made that clear before, that I'll almost always remove on what I'm operating as. That is to be understood, because either way you are seeing that the notation is getting too much out of hand. So I've just removed that x alpha, the evaluation part. So but you can understand that in fact if you evaluate this at x alpha, so the application, if you want to apply some function on one of these test point, you do the usual thing. And what I mean by that is you do this. So that is how you usually avoid writing the test points and just deal with the functions. So that I will actually introduce a new term called the error, which will be defined as this one. Okay. So now of all, so we had a very long list of parameters. We have given how the gradient descent would work for the parameters, those are in the last layer. Now what I wanted to say here is that one could redo the entire thing for each of the layers. But then the computation would not only get complex only in notation, but also in terms of how much computational power you are using. So all of these are supposed to be done by some computer, and you have a limited amount of memory that you can use, RAM that you can use, and at the end of the day, someone has to pay the bill. So we need some better, efficient way of carrying out the change, or whatever this term would be for all the other layers, that is before the last layer. But what is in fact true is that whatever we are doing is actually equivalent to the normal way of doing it. So the so okay, it will be much clear if I write down. And here is what all the fuss is about back propagation. So here is something I will write, and I will expect everyone will understand, although it is not really clear why someone will ever think of it. So what I'm claiming here is that the parameters at any layer for all L, that is not the last layer. So this is your last layer. You say that the changes of the parameters in those layers are dependent on the changes that you have made on the layer after it. So it would be intuitive if we had replaced these L's with L plus 1. So you are at the L plus 1th layer, and you say whatever the changes in parameters of L plus 1 will be is dependent on the changes that we have made in the last layer, that is on the Lth layer. But here I am doing just the opposite. Now what can be proven is that whatever I am going to do, the result I will get is equivalent to what the forward direction would be. So the forward direction would be, if you want for the L plus 1th layer, what you should do is, that depends on the last layer. This is what the forward direction would be like. But I'm saying the opposite. I'm saying that the parameters in the Lth layer, the changes there depends on the parameters of the L plus first layer. In fact, what can be shown is that the calculation that I'm going to work out here are equivalent to the calculation that would be done here. That's the point, which I will not actually show here. But anyways, I'm going to do the back propagation. So for that, I have to write down. So zk of L plus 1 is this. Again, AP of L is the thing that you get after you put the nonlinear activation. So, okay, one thing I want to comment here. Does this thing, for example, if this L was L minus 1, can you imagine we have actually calculated this thing? And it is in fact here, this term. If your small l was L minus 1, then this term and this term are the same thing. In fact, this one. Is that clear? Anyone? I think that's clear, no? So for the last layer, we have calculated this one, and then we have come to the L minus 1th layer, and for that we have already done this one. All we need to do is find this term. This term is all that remains to be found. So that is what I'm going to do. So I'm removing this the ranges of the indices. That is this one only. So from L plus 1. And this part would vanish because that's constant. That does not constant, that does not depend on Wij. Okay. So that would be like, okay, now one thing. Should have written it here. Now, do you understand that there is only one of the W's that is in fact dependent on this? The others would actually vanish. Sorry, that was my wrong. There is only one of the APs that actually depends on this Wij. In fact, which one? That's just AI. AI of L is your nonlinear activation of Zi of L. If you expand this Zi, so then you would, if you expand this Zi, then you would get all these Wij terms. So this in fact simplifies. So I have differentiated. Okay. So this is nothing but the differentiation of this. And then I have to compose the differentiation. What is this? Sorry. Now I want to resubstitute it back here. All I have done is resubstitute this one into this one. So I've substituted 1 into. This one was your delta. So that is your delta K. Then you have delta W Ki L plus 1, and then you have your K going from 1 to N L plus 1. Have I written that here? Yeah. So okay, these two I have just brought out because these indices does not depend on K. So they are common to all. So they have come out. And we are almost done. So this actually simplifies to, okay, this actually simplifies to aj of L minus 1 times delta I of the layer. So we made all this fast to show one thing. For the gradient descent, we needed this term for each of the L. For the last layer L, it was easier because we could do it explicitly. For all the layers before that, what I said was to do a forward direction differentiation would take a larger computational cost. So what we said is that we will do the opposite thing. We'll say that the changes in the parameters for some layer L, which is not the last layer, depends on the changes of the next layer. We could not have made that argument for the last layer. So we had to do this kind of differentiation. But for any layer that is before the last layer, we could iteratively build this relation. All that says is that the change that you need to do in the parameters of the any layer that is not the last layer is the nonlinear activation of the previous layer, which you know, and the error. This is what is called the error function of the next layer. And now you can actually write this for all L is equal to 1 to L minus 1. So, and similarly, I have not done this explicitly, but you could have made the same argument for this one also. Yeah. So that is the entire mathematical formulation for all these back propagation business. So I think in the first paper where they actually introduced back propagation, they have also again hinted that this way of doing the differentiation is equivalent to the usual way of doing the differentiation, but it actually takes some effort to show that the answer is same. Because in fact, so what people do is take 2-layer network and then show that they are same. That one can actually try out. Okay, so that was one part. So I have actually hit 2 of my goals. I have actually told both of them. Now one thing. Okay, so once we have developed the entire gradient descent business, okay, it's already 6:40, I have 20 minutes. So once we have already developed the iterative equation and how the gradient descent works, the following comment I want to make. So these are all hyperparameters. All of these wij's of each layers and all these bases of each layers. So these are all all of the hyperparameters. And we are saying that we will actually find the best hyperparameters through this gradient descent kind of business. So we have skipped one part, which is initialization. Now, generally in what we did in both MLF also, when this gradient descent was being taught, is that we said that we can take any initial values and this will at least converge to one of the saddle points. Now that is where there is an issue. So mostly we took something like 0. So one of the easiest kind of a initialization one can do is initialize all the hyperparameters to 0. But what happens is that if you initialize all the hyperparameters to 0, there is this symmetry that you won't break. What is that symmetry? Is the following. You have your network where you have invested money, or you have actually mathematically made your model where there are multiple neurons in each of the layers. What can be shown is that if all of the initial hyperparameters are set to 0, then even if we apply the gradient descent, our entire model with so many neurons in each layer would work as if there is a single neuron in each layer. So you have a very complex model and you want to understand very complex kind of functions, but that you can't achieve by a single neuron in each layer. A single neuron in each layer would at most give some kind of a composed nonlinear function of the initial variable. But that amount of complexity is not only very less, but it is nowhere enough for the task that we generally give to deep learning models. So in fact, you cannot just set all the hyperparameters to 0. So there are 3 ways in the literature that has been prescribed on how to set these hyperparameters. One is to use, this was a bad start, but the idea was not completely bad. So what they do instead is they take each of the parameters to be randomly sampled from a zero mean Gaussian distribution. The other 2 ways are, one, what is called it, so 3 ways for initialization of hyperparameters. One is your constant, which is again bad. You can't take a constant, you can't do the constant. That you face the same issue as 0. You can't take everyone a constant, everyone same constant. You can't do that. The other way is this Gaussian zero mean. The one is this truncated Gaussian, again zero mean. And the third one was, I have to check, I did not write. So the third one was uniform distribution. So you can't do constant, but you in fact can do uniform distribution. Now, the entire theory that has been developed in the book has taken this route. The authors have commented that, so to define any of them, for Gaussian you would generally need a mean, so that we have set to 0, and you would need a variance. What they show is that for enough wide networks, all 3 converge to the same thing. That is what they expect. It is not very trivial to show it. In fact, even they have just commented central limit theorem, by central limit theorem, but that actually does not work. It is quite difficult to actually show that even if you do some uniform distribution sampling for a wide enough network, the statistics for some layers, some very deep layer, will be the same as if you had, even if you had chosen a Gaussian distribution kind of sampling for the initial hyperparameter sampling. Okay, I just jumbled the word, so I'll just restate it once more. It is difficult to show. In fact, it is non-trivial to show that the effect at a very deep layer are same for both uniform and Gaussian. It is in fact non-trivial to show. That was one comment, but it okay. So this one is actually easy to show. If you set each of them 0, the exercise is to take a very take a just 2 or 3 layered network, and what you will see is that each of the neurons, each of the parameters in the layers will all behave same. So for all neurons, for each of the neurons here, where is the picture? Okay, yeah. Each of the neurons have a associated Wij and a Bj. If I had initially set all of them to 0, what would happen is the changes would be same for each of the neurons. So it in fact would behave as if it is some linear combination of a central limit theorem are exactly the same for each of the neurons in a single layer. And that essentially concludes that you can't break that symmetry. Okay. So I have given you two things, that how this hyperparameterization, initialization for the hyperparameters would work. So for Gaussian, what we do is we have this expected value. So to give a Gaussian, you need to know the mean and the variance. The mean is 0. You would independently actually sample. So this is a very fancy way of writing it, which is you take some CW and you have to do some rescaling for some layer L. Okay. So this is what we told known as Kronecker delta function. Okay, so this delta has nothing to do with this error function. Okay, this error function I have also denoted by delta, but this is different. This is the Kronecker delta. It's not the same as that error function. Okay, so it is some CB, and you don't need a normalization here. I will not have the time, but there is a good reason why you want this NL minus 1 here. Okay, so okay, these, so it's very easy to see. If you want to write in the distribution form, the distribution form is this. So you are sampling your BI from a Gaussian distribution of 1 by root over of 2 pi CB of layer L, and you have some exponentiation of minus 1 by 2 . Again, you have to understand that there is some evaluation here. Okay, so that, and similarly you can do it for Wi and J. So you independently sample for each of the parameters, you independently sample them. They are independent Gaussian sampling you are doing here. Okay, so, and there is a similar way for writing this also. 650. Okay, so before I end, here is a last piece of comment. Now we want to actually, so we have this as the output. Now it is clear, or it should be clear by now, that this is a function of Wi's and Bi's and something, a very big function of compositions and composition, multiple composition, and each of them are random variables actually. So the output is in fact not a single thing, but a random variable in itself. So what we want to look into, or the entire motto of developing an effective theory, is to understand this very distribution, which for even very simple cases is too damn difficult to do. Because if you, so think of all the parameters as theta mu's. Okay, so I'm not writing them as Bi's and Wi's respectively. So you would have to calculate this kind of a integration. So yeah, you have to calculate this kind of a integration. And for example, the issue is that this in fact is kind of a deterministic system. But you have that as a probability. So you have something that is deterministic. For example, if you have some D and you have chosen some parameters, then you can, there is no probability essentially associated with it. it is in fact deterministic. It is very hard to do, but you can in fact just carry out the model. For example, here are these are okay. So these are the equations. So if you fix some x alpha, then there is only a specific output to it after some, after you have efficiently fixed your parameters, but it's still a deterministic part. So in fact here what the authors do is introduce something called as a Dirac delta function, and then the theory slowly gets more and more complicated. So maybe I have tried to provide you two things here, that you have some exposure how difficult this is going to be, and you can actually now decide that if you want to get into the book or not. So in fact, next the book develops some steps in which you can study what they call as a deep linear networks. In fact, all that they mean by deep linear networks is that they remove this nonlinear activation. So you don't have this sigma anymore here. You don't have this sigma. And they try to develop some things. For example, these parameters, for example, they prescribe some things. For example, here, this has to be a very specific value. In fact, this has to be 1. So the variance of a particular parameters in lth layer must be 1 by the number of neurons in the last layer. Otherwise, either your output of the model gets too much, it fluctuates too much, or if it is less than 1, you get very monotonous output. So that's one of the prescriptions that they give for deep linear networks, which are essentially useless. That's the next chapter, but they have outlined some steps which then they follow out for a purely general MLP, multi-layer perceptron. In fact, they can't do it fully. It's still under research. They do up till initialization. I think they do everything for multi-layer perceptron, but for transformers, it's still under research too. Okay. So what they do in the deep linear networks is they prescribe a generalized method to look into some model that they particularly do for the deep linear networks. Then the rest of the book is completely dedicated to carry out those same steps for the MLP case, which is not very tricky. And then they provide some directions to carry out for transformers. So, yeah, that's the book about, and this was the second chapter. Essentially, I've covered everything there in the second chapter. This was not really a good talk, but anyways, any questions? I mean, I'm done. There is nothing more to say. So any questions or anything? So I've actually pinned the book in Meet chat. I think I've said that. Okay. So there is one thing I need to do is anyone who is interested there is this feedback form that I would like anyone who has attended today to actually fill it. This is required for your participation certificate. Anyways, so that was it from my side then. Maybe any questions? I'll wait till 7.